Poi mutono. Okay, we can start. So we talked about adding vectors. So we had a vector here. Okay, what did we say a vector was? It has two things. Yeah, magnitude, direction. It's a magnitude and direction. So how do we represent a vector? An arrow.
Next, how do we represent a vector, Quisky? Professor, just so you know, there's an echo today. I don't know what it is.
There's an echo. Okay, let me turn this off and turn this back on. No, I don't hear it. But that doesn't mean, let me do this, and let me do this. Okay, I turned it off and back on. Did that have any good effect?
Gosh, I still hear it. I mean, we can keep going. I just thought I'd let you know. It's different than usual.
I'm not certain what is causing it though.
Okay, boy, I can't think of anything either.
That is bizarre. Okay, I'm sorry about that. Hopefully it's not too irritating. It sounds like it'd be very irritating actually.
Okay, we'll give it a whirl. Thank you.
Okay, so there's a vector there. What do we call the length of the vector? Magnitude. So the length is magnitude. How do we denote this? So this is a vector v, and how do I denote it? I take the v and do what to it? I put that half arrow over it like that. That's a half arrow. And how do I denote the length? Yeah, they have some values in this here. So the actual length here is going to be this. And then the direction is given by, then the direction is pointing. Okay? Now, how do vectors add? So if I have A plus B, and if A looks like this, that B looks like that, how do vectors add? A tip to tail. Do you have to start with this one, or do you have to start with this one? Doesn't matter. So I'm going to start with B here. So if I want to make a new vector here, this. Okay, B is this. Okay, now how do I add A to it? I take the tail here, and I add it to the tip here. So I put my A over here like this. Now where does C go? Does C go this way, or does C go this way? Yeah, so the actual, this one right here goes like this. That'll be C. If I go the other way, what do I have? I did have minus C. Does that all make sense? Okay. Now, we said we wanted to talk about a vector as being made up of basically something else. We call these something else's, we call those components. So we can think of a vector as being made up of other vectors called components. And we had some rules on the components. What were the rules for our components? Components must be to one another, so all the components are perpendicular to one another, so components, by definition, are perpendicular to one another. And then how do we take them? Along the x, y, and then z axis as well. I'm not going to put in the z axis until a little bit later today, but there could be a third component as well. So further, components, by definition, are taken from the x, y, and z axis. So that means I can write a vector here, A, has some x component, plus some y component. And in principle, there would also then be a z component, but I'm not going to put that in right now. I'll put it in a little bit later, but not right now. Okay. Any questions with that? So if I write a vector A like this, my x component is this fellow. My y component is like this. Right? So what did I do with A and y? I added these in a tip-to-tail fashion. So I took this vector and then this component and this component, added them in a tip-to-tail fashion, and that gives us this vector here. Does that make sense? Okay. So what can we do with that? We could do the following. So if we write each vector in terms of its components, we have, so let's do this. So let's say this. And let's say that A looks like this. And let's say that B looks like that. No, I'll go like this. What does this now mean? I can write A as Y. I can think of this vector here, A. I can think of this as being this vector here, the X, plus this vector here, the Y. Right? This vector plus this vector equals that vector. Then what kind of view B is being made up of? Yeah, so B, my friend here, is really this BX here. Plus this, my BY here. So this vector plus this vector makes this vector. So if I add these two in a tip-to-tail fashion, I get this. So when I add the whole thing together like this, I get AX plus AY plus BX plus BY. And then what did we do yesterday? Yeah, we're going to take this vector and do the same thing. And then we did one more thing on this side. What did we do? Yeah, we put all the x's together and we put all the y's together. So we're going to take this x and this x. And then group these two together. And if I were to look at that, what does that mean? That means I take this AX plus this BX. So that's taking this fellow plus this fellow. Okay. And then what does this say? This says add this vector here, there, plus this vector here, which is bigger, like that. That's what that's saying. So if you add those all together, or you just add these in a tip-to-tail fashion. AX, BX, AY, BY here, and then this has to be C. But then what does that make this? That has to be. That has to be my friend CX. So this here has to be this. Okay. So CX is this fellow. And that makes our friend here CY. That means that this fellow here is that fellow here. Does that make sense? Questions with that? Now, you most likely have seen that in high school if you've had this, and if you've had physics in high school. What I've told you is really nothing overly profound. But it does show you very systematically why you can do this. Now, the next part you may have not had in high school. And you want to write these x and y components in kind of a weird fashion. And this is the way actually you're going to write vectors for the rest of your life. And it looks a little weird. It's going to seem more like bookkeeping. And at some level, a waste of time and kind of stupid. It's going to look like I'm overly complicating things. It turns out I'm not. It turns out as you take more sophisticated courses, you do a lot more with this notation. But when you're learning it right now as freshmen, it really comes across as looking kind of stupid. So I want to show you another way you can write these. So any questions on this before I erase? Okay, so the components. Of a vector can be written in terms of unit vectors. Okay. There are three common unit vectors. I'm going to give you the, I'm going to tell you why they're called a unit vector. Okay, they are I, and then you put this little caret on it. This little caret symbol is called a hat. So you'd call this I hat. Okay. You have another one called J hat. And then the other one is going to be called K hat. Okay. This is how they go. The length of any unit vector by definition is 1. So if you have a unit vector, it doesn't matter what kind of unit vector you are, you by definition have a length of 1. So the magnitude of I hat is 1. The magnitude of J hat is 1. And the magnitude of K hat is 1. Okay? They also have no units. These are dimensionless. I can say they're unitless. Now, by definition, I hat only points along the x-axis. J hat only points along the y-axis. And K hat only points along the z-axis. So let's write that down in the real picture. So by definition, I hat only points along the x-axis. J hat only points along the y-axis. And K hat only points along the axis. So let me just start with I and J first, then I'll put in K. So this is what this would look like. So here's Y, here's X. What would I hat look like then? It's going to look like this. That's I hat. What's its length? 1. And it only points along the x-axis. How does J hat then have to look? It's going to be along the y-axis. Okay? Now, I'm going to do another axis like this, kind of put them all together. This is X, this is Y, this is Z. Okay, what does this represent? How does my x-axis actually go? If I draw this on the border, what does that represent? Yeah. Exactly. It's going to be going in and out of the board. In this case here, the way I drew it is it in or out? It's going to be coming out like that. That's what my x-axis is going to do. Okay. So you know when you're little kids and you're playing cops and robbers like this, really what this is getting you ready to do three-dimensional vectors. What this was, it's actually not a gun when you're a kid. It's really a metaphor. X-axis, y-axis, and z-axis. Crazy. Wow, you learn so much. Okay. How does I hat? Yes. Yes, and that's actually not an accident. Because it turns out we're going to get something called a right-hand rule. You're going to be doing a lot of this. Oh, we're going to be doing a lot of this semester with this and all this other stuff. Next semester, we're going to have right-hand rules coming out of our ears. And it's all going to be connected to something we're going to call a cross product. So we're going to be getting that. So how would I have to look here? I hat would be this. J hat. This guy. And then K hat is like this. Okay, the next point is kind of subtle, and don't worry a whole lot about it. But it's one of those points stick in your head at some point. This coordinate system is called a right-handed coordinate system. A right-handed coordinate system is anything that looks like this or a proper rotation. So if I grab this and kind of rotated it, they would all be right-handed coordinate systems. We're going to set up things later on. We're going to multiply vectors. And it turns out that if you don't have a right-handed coordinate system, it's not going to work. Okay? If you switch this, if I put the y here and the x here, that's called a left-handed coordinate system. And we're not going to use those in this course. Okay? So these are the unit vectors. Now you could say, well, how is this useful? Okay, let's see how it's useful. So how are unit vectors useful? Okay, well, let's say we have this. Let's take an example. Suppose I tell you that vector A is 5i hat plus 3j hat. So suppose you're going to, again, Valentine's Day is coming up, you can't find chocolate, so instead you bring your date a vector. So you go down to Wegmans, down the vector aisle, you put this vector in your cart. What kind of vector did you buy? Let's draw it. Okay? What does this mean? Yeah, what is this going to be? Well, if we draw it out. This fellow here is I hat plus I hat plus I hat plus I hat plus I hat. You have 5 of them. So if you're to draw this, you'd have I hat, I hat, I hat, I hat, I hat. And that's what that would be. What would then be 3j hat? Yeah, this fellow is going to be, this is j hat plus j hat plus j hat. So the I hat only goes along the x-axis. These only go along the y-axis. So this one is going to be j hat plus j hat plus j hat. So this vector would really look like what? This vector would look like that. So really, what is this? This fellow right here, this is nothing but my AX component. And this fellow right here is really my AY component. So all we did was write the X and Y components in kind of a weird fashion using unit vectors. Again, when you first learned this, it looks like you've greatly complicated the problem. You made it a lot more complicated than it could be. And at this level, that's true. It's not going to be as we do more sophisticated things. As we do more sophisticated things, and they're going to, you need this notation. And not only that, you don't realize it with your level of physics, but when you take more sophisticated physics, this idea here gets basically kind of put on steroids and becomes actually quite profound. I'm teaching a course in general relativity, gravity, black holes, cosmology, all that. And we're basically looking at the four-dimensional version of this. It turns out to be quite useful. It turns out to be hard. You have to be really good at this. And you do 2 dimensions at a time. Okay? So what would be something like this? What would be A equals, let's say 2I hat plus 3J hat plus 2K hat? What would that look like? Let's see if we get. I should have brought more markers with me. I think they, yeah. It'll work. Okay. Okay, so what would this mean? What would be 2I hat? Yes, in other words, again, if I draw my coordinate system, X, Y, Z. I have I hat here, I hat here. That would be this one here. What would be 3J hat? J hat, J hat, J hat. So if I have a little markers here, what would this be? This fellow here, let's say this is I hat. So I have I hat, followed by I hat. Then I have the J hat, so then I have J hat, J hat, J hat. What about my 2K? Be 2 vertical like this. It'd be K hat like this. So what you would have I hat, because this is my x-axis. So now I'm here. J hat, J hat, J hat. This is my y-axis, so now I'm here. And then K hat, like this. So now I would be here. So where would be your vector then? Yeah, you'd start here at the first vector, and you go to your last vector. That would be your vector A. So in this case here, where we have I hat, J hat, J hat, J hat, K hat, we'd have a vector going like this. So our vector go like this. Does that make sense? What would be the following?
You always start at the origin.
Oh, you can actually put them anywhere you want, but usually in a case like this, when you're just dealing with one vector, you put it at the origin.
Okay.
But you can put them anywhere you want. Okay. What we have is suppose I want you to draw this. What would that look like? So this would be, here's your y-axis, here's your x-axis. We know the I hat is like this. That's I hat. But what do we have? Minus I hat. So what happens when you take a minus of a vector? You switch its direction. So this is minus I hat. And what are we adding to it? Yeah, J hat plus J hat. Here like this. So our vector is actually this guy here. So let's try another one. Let's say you have vector A here, which is minus I hat plus 2J hat. The vector B here is going to be 3I hat minus 4J I want you to find C equals A plus B. What would that be? Oh, just set them. Okay. So you have C. Here's my friend A. So I'll put that in here. Here's my friend A. Here's my friend B. What would you do with that mess? Yeah, you'd group all the I hats together, and you group all the J hats together. So if I had minus I hat plus 3 J hat, this is going to be 2 I hat. Okay, what about the J hats? Two, then minus 4, so this is minus 2 J hat. So what does this look like? Try to say draw this. What would you draw?
It goes due to the.
You're going to have this guy here, this is 2 I hat. How does my J hat go?
Goes down.
Down. And so this right here is my friend C. What is my X component of C? What's the X component of C?
2i.
Yeah, 2 I hat. So it has the length here in the X direction of 2. What about in the Y axis? What's the Y component? It's going to be minus 2, going down that way like this. Does that make sense? Now we can do a couple more things here. How am I doing on time? Oh, I'm done. Let's take another example. Let's say, so let's say you can't find a vector at, Wegmans for Valentine's Day. So you go to Lowe's and you're going to construct a vector. So you go down the aisle of Lowe's and you find this vector here, has a length of 10, it has an angle of 30 degrees. I want you to write A in terms of unit vectors. So in other words, I want you to have A is some AX I hat, where AX is some number, plus AY J hat, where J is some, where AY is some number. I want you to write this vector like that. So how'd you do that? Hopefully this doesn't mess things up.
You can translate the magnitude of A by taking the cosine of theta of the value of magnitude.
Why? That's completely correct.
Because basically cosine of theta of A can basically be the vector along the x-axis.
Okay, so what would be the first thing? Everything you said is right. Do something first. If I give you this information, what would be the first thing you do? Yes?
You draw it.
Always draw it, okay? This sounds like a really dumb thing to say. The most important thing you do in physics is draw a picture, which sounds completely stupid. It turns out it's not. Usually when you come by and you actually ask for help on something, I'm going to look at your paper. I'm probably going to hand it back to you, and I'm going to say the following. I'm going to say, tell me why I already don't like your paper. And you're going to look at me cross-eyed like, I don't know. And it's always the same answer. Here's what I'm going to tell you. I'm going to say, I don't like your paper because I don't see a picture. So always when you do these things, draw pictures. So if somebody gives you this, you draw that picture. So come over here. Here's a vector here like this. The length of this fellow is 10. Here's my y-axis. Here's my x-axis. And I know that this angle here is 30 degrees. Always draw your picture. Now, if I want it in terms of x and y components, I want to then draw the x and y components for this. So if you have a vector like this, how do you draw the x and y components? There's an easy way to do it. Go to the tip of the arrow and drop a perpendicular to your x-axis here. So I'm going to go here, I'm going to drop a perpendicular like this. That's a perpendicular. Then what does it mean? What does that distance there have to be? In terms of our variables here. It has to be AY. This is my y component. That's going to be, this will be how far it's going in the j direction. And then what about this fellow over here? That then has to be the x component. Okay. Now, the convention is whenever you draw a component, usually components you always draw with dotted lines. Put a little arrows on them too. So this dotted line here, I'm going to put an arrow here, so that's going to represent my x component. Then I'll put a little arrow here, that's going to be my y component. So by convention, you draw components with dotted lines. Okay. So let's figure out how to do this. So if you look at this, here's a triangle, okay? If I want this side here, this is what part of the triangle? But here's my angle. That's the adjacent side. Okay. This is the hypotenuse, this is opposite. Okay, so let's go and do a little review of our trig. So first of all, when you do trig, what does it assume about the triangles? They have to be right triangles, and the reason you want right triangles is that then the ratios will always stay the same, independent of how big or small your triangle is. So if I have a tiny little right triangle, and a really, really big one but has the same angle, it turns out that all those ratios will stay the same. So the main ones are going to have a sine of theta, cosine of theta, and tangent of theta. Okay, sine is what? This is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Like that. Okay, and those you just want to know. Okay, at some point, you know, you're going to write SOHCAHTOA on your paper. Okay, at some point, you're going to reach the point in your education where these are just going to be so obvious, you don't have to write SOHCAHTOA. So if you're still writing SOHCAHTOA, that's fine, but get to the point where they just can't be anything else, where they're just going to burn into your head. Okay? So if I want to find this side here, which trig function do I want? I have my hypotenuse. This side here is the adjacent side. So I'm going to want to use my friend the cosine. So I'm going to say cosine of 30 degrees equals my adjacent side is my friend AX. My hypotenuse here is my magnitude of A. I take over my magnitude of A, so that tells me that AX is magnitude of A cosine of 30 degrees. So what do we get for this? We get 10. What's the cosine of 30 degrees as a fraction? Square root of 3 over 2. So this is 5 square root of 3. Okay? Tell me how to find AY. Yeah. So if I go over here, now I want the opposite side. And so I have the hypotenuse. So now I'm going to do a sine. You're going to say sine of 30 equals what? Equals my opposite side over my hypotenuse. This over here. So this tells me y. It's magnitude of A sine of 30 degrees. This is 10. Sine of 30 is 1/2. tell me how to write my vector A then. My vector A then. In terms of unit vectors is what? So 5 square root of 3 pi half plus 5j half. That's how you would write it. That makes sense? Okay. Let's try another one. Okay, how are we doing on time? Doing fine. Okay, let me say about the angles you're going to need, and then so the angles we will use repeatedly. So memorize these. All right, okay, let me get on my soapbox here and criticize something. Okay, when you have actually the word memorize always has a bad connotation and it really shouldn't. As it turns out, if some things just aren't known in your head, just where you can just rattle them off immediately, or you just kind of know, you really can't do a lot of things in life. If you have to say, let me look this up, let me look this up, let me look this up, if you're doing this on everything, if you don't have anything in your head, you're not, it's not going to work. You can do that with a couple things, but there's some things you just have to have in your head. Okay, actually more than a couple things. You also can't do a language. If you want to speak another language, if you don't have vocabulary memorized, you can't do a language. You can't even engage in a debate with anyone. You say, well, there's something I want to make. I want to make a point here. Well, let me go look up that fact. No, you can't do that in a debate. So don't let people criticize when you say memorize. It always has a negative connotation. But as soon as you don't understand it, and that's nonsense. Just because you have something memorized doesn't mean you don't understand it. Okay, I'm off myself. Fine. Okay, so what are the angles we need to know? Yes. 0 is a good one. What else? 30. 45. Okay. 90 and then 60. Okay. They're the ones you want to know the sine, cosine, and tangent for all these angles here. Okay? They're going to be the main ones we have. Okay? I'll go and show you how to do them, but just so you know, these angles are going to occur all the time, so you might as well know what those values are in your head. Okay. I'll show you actually how you get these. They're actually trivial. Okay. What did we say that was? 1/2. What was this one? Go to 3/2. Okay. I'm going to give you 2 others. What about sine of 60? 3/2. Cosine of 60? 1/2. Why? Why are those values those? You could say, well, that's what my calculator gives me. That's not a good answer. There is a triangle. Yes. How do I know that? How do I know that? I can draw that unit circle, but it's not obvious to me that I get the half of it. Yes. Which other triangle do you draw? Okay, for those ones here, we're going to do that. There's a special triangle. I just want to show you where these come from, because I don't want you to think that things just come out of the blue. Okay? Equilateral triangle. If this is 60, if this is 60, this is 60. Okay. What do you know about the sides of all the triangles of an equilateral triangle? They're the same. So we're going to pick a value that works out well. 2, 2, 2, 2. Okay. How can I now get in my 30 degrees here? What am I going to do to up here? I'm going to cut it in half. And I cut this in half like this. Okay? If I cut that in half like this, what am I left with? Left with 60. This is 2. What is this side right here? 1. And this is that's the 90 degree. Then this angle here is 30. Okay, tell me what this side is. Yeah. Square root of 3. How'd you get it? Yeah. Yeah, but we can't use the answer to get what we want to get. Okay. Okay, you have a right triangle. What do you have? Pythagorean theorem, right? So this is side C, if this is A, if this is B. Now that C squared equals A squared plus B squared. So this is 2 squared equals 1 squared plus B squared. So this is 4 minus 1 equals B squared, or B equals square root of 3. Okay. Okay, you tell me where all these come from. What is the definition of sine of an angle? No, not sine. Sine is, yeah. Opposite over hypotenuse. Okay. So what do you have here? Opposite, square root of 3. Okay. Over 2. That's what you get for this guy. Okay. What about the cosine? Adjacent over the hypotenuse. Adjacent over the hypotenuse. This is 2. Why is the cosine of 30 degrees the square root of 3 over 2? Here's your angle. Okay. Where is the adjacent side of here's my angle? Here's my angle. This is the adjacent side. Right? So I have square root of 3 over 2. That's square root of 3 over 2. What is the sine of 30 degrees? One half. So if here's my 30, my opposite side is here 1. Here's my hypotenuse 2, a half. That's why those values are what they are. Okay, it's quite nice. Questions to that? I just wanted to see where things come from. We'll do the cosine ones again, but we have 5 minutes. Let's do another example. Oh, well, let's do the cosine as well. Then we'll do more examples tomorrow. Okay, cosine of 45. Yeah. Square root of 2 over 2. Sine of 45. Same thing. Why? Yeah, here we're going to look at an isosceles triangle, but an isosceles right triangle. So in a case like that, you can look at this right here. This is 90 degrees. If that's 90 degrees, what do you know about these two sides here? They're both 45. Okay, we're going to make this side 1 and this side 1. Right, because in an isosceles triangle, the two sides are the same. What does that mean, this side thing? Square root of 2. Right? This squared plus this squared, the square root of doing this. So don't just kind of tip it on its side, and you're good to go. Okay, how do you define cosine? Adjacent over hypotenuse. Okay. Normally, you don't leave square roots in the bottom, so what do? Multiply top and bottom by square root of 2. So this is square root of 2 over 2. The sine sign is an opposite over hypotenuse, and it's the same thing. Same thing. That make sense? Okay. So that's where those things come from. Okay, let's try another example. Okay. So let's say we have a vector A, which is this. Vector B, which is this. And vector C, which is and I want you to find the new vector D, which is 2A minus B minus 3C. Okay, by this I want you to write the unit vector notation. Okay. You tell me what to do. And let's say we're giving it time. Okay. I'll let you go. We have 1 minute left. Use your minute wisely. Take about 30 seconds to think about how you'll use your 1 minute. Okay? Enjoy your day. See you tomorrow. We're going to start with this one tomorrow.